Okay, good morning, viewers. Good morning, students. This is Supreme Education Foundation Schools, Year 11 Mathematics class. We've been talking about probability, and today we shall be talking about the topic relative frequency. My name is Mr. Ayodeji Ogunyeye, and I'll be your tutor today. All right, the objectives are understanding and calculating relative frequency, creating a relative frequency graph, and also using relative frequency to estimate probability. Let's get right to it. Now, relative frequency is a tool we use in probability to work out how likely events are to happen. Sometimes it is hard to find how likely something is to happen. It is often suggested that if you drop a slice of toast, it always seems to land with the butter or jam side facing down. Okay, but that makes sense, because if you take a slice of a toast, of a bread, and you put a butter on it, okay, of the jam, it makes that side of the toast heavier. So obviously, it's more likely that, when you drop it, the butter side or the jam side is definitely going to face down. Okay, but what about the jam side facing up? How can we find the probability of it landing jam up? And that is what we are looking at. One method would be to keep a record of how many times you drop your toast and how many times it landed jam up. Using this result, it would then be possible to estimate the likelihood. Remember, we mentioned that in one of our lessons, likelihood also means probability, also means chance, okay? The likelihood of it landing, so the probability of it landing jam up. Now, relative frequency equals to the number of times it lands jam up divided by the number of times it was dropped. Okay, we're still going to give a general formula for relative frequency, but this one is defined. This formula is defined with respect to the illustration that we're giving you over here. Now, we have a slice of jam on toast. Okay, that's a slice of jam on the toast that you're looking at, right? Jam is the red part of it. It has been dropped 10 times and landed jam up 8 times. Find the relative frequency of it landing jam up. Of course, we've seen the experiment, we've seen the outcomes. The total number of outcomes, possible outcomes, which is in this case of experiment, we call it the total number of trials, the number of times you performed the experiment. So it was done 10 times, and then the number of successful outcomes, which is what you really want to see, your required outcome, the number of successful trials in this case of relative frequency, we have 8 times for that. So definitely 8 out of 10, relative frequency is 8 over 10. If you are following my explanation, you realize that this is just like the normal probability that we know, but then this one has experiments attached to it. So you'll be talking about trials, trials, trials. Now, the relative frequency of landing jam up after 10 trials is 0.8 conclusively. We want to show how to plot the graph of trials against relative frequency. This comes from your knowledge of graph plotting. Now, this point, the first value in this coordinate is for X value, and the second value is for Y value. From your knowledge of Cartesian plane, or the XY plane, you remember that this is meant to be for the Y-axis, while this is meant to be for the X-axis, okay? So values of X horizontally, values of Y vertically. So if you apply that knowledge, it simply shows, or it means that 10 basically over here Okay, we'll expect 10 to be here on the x-axis and then 0.8 on the y-axis. So when we trace that, we find that we're just going to drag the point. 10 coinciding with 0.8 is right here. So that is where our point is. Okay. Now, if the toast gets dropped another 10 times, in total, it landed jam up 12 times. You see that? We did 10 times before, now another 10 times. That's going to make it a total of 20 times for the total number of trials. But the total number of trials, of successful trials, let me repeat that. The total number of successful trials after the 20 times of dropping it is now 12 times. So the relative frequency is supposed to be 12 over 20, which is 0.6. To plot the value on our graph, x-axis goes for 20, 0.6 for y-axis. As you can see, on the x-axis is our number of trials. On the y-axis is our relative frequency. I'm going to drag the point. 20 goes together with 0.6, so I have it right here. Well done. Okay, let's move on. Now, let us work out, okay, the table below shows the result of a piece of toast being thrown 10, 20, 30, 40, 50, and 100 times. Let us work out the relative frequency for each row. When you get the answer correct, you can plot the point on the graph. Remember, relative frequency is the number of times it jammed up over the total number of drops or total number of trials. So for this next one, it's going to be 15 over 30. We put a value here. I see that should be 0.5. Okay. And then we can plot the point. What we are plotting, don't forget, is relative frequency, or the number of trials, rather, total number of trials, relative frequency against the total number of trials. So 30 for x-axis, 0.5 for y-axis. So I'm dragging the point to 30 on x-axis and taking it to 0.5 on y-axis. Next point. This will be 18 divided by 40 to get the relative frequency there. 18 divided by 40, and that is going to give us 0.45. So we put that in there, 0.45. So we can plot the point. Let's drag the point. I have 40 and I have 0.45. 0.45 is in between 0.4 and 0.45. It's in between. So that's why I put it in the middle here. Okay, the next one. 21 divided by 50. 21 divided by 50 is going to give us 0.42. 0.42. We plot the point on our graph. That is for 50, and then 0.42 is just going to be a little bit away from 0.4. Okay, and then the last one we have 38 divided by 100, which should give 0.38. And plotting the point for that, we have 0.38 is just going to be a bit close to 0.4. Right there, 0.38. So that is our graph. All right, let's move on. Now, we have a light company that is testing samples of its light bulbs to see how long they last. The company tests 250 light bulbs and finds that 75 last for less than 800 hours, 50 last between 800 and 1,200 hours. The rest lasted for over 1,200 hours. We want to estimate the probability that A bulb lasts less than 800 hours. A bulb lasts less than 800 hours. Of course, if it's less than 800 hours, the successful outcomes for less than 800 hours is 75. Total number of trials is 250. So the estimated probability is going to be 75, okay, divided by 250. 75 divided by 250, and that is going to give us 0.3. So the answer here is 0.3. 0.3. I'm sure we all understand that, and I'm going to quickly put that up immediately to show how that was calculated. We got that to be equal to 75 divided by 250. Okay, that is how we have calculated our 0.3, which expectedly we would expect it to then be equal to the 0.3 that we have there. So take note of that, guys. Very necessary. Okay. The next one. A bulb lasts longer than 1,200 hours. Okay. Now, for those bulbs that lasted more than 1,200 hours, how many are they? We need to know. That is going to be our number of successful trials. They just told us that the rest lasted for over 1,200 hours, and that is the longer than 1,200 hours. So we need to calculate the rest. And to calculate the rest, I think what we just need to do is just to subtract the addition of 70 and 50. Okay, so that's going to be, the rest is going to be 250 minus the sum of 50 and 75. I can put that in bracket. The sum of 75 plus 50. So I'm going to expect that to give me the result I want, which is 250 minus 125. And when you do that subtraction, you are going to get, I think, 125 back. Yeah, that's double. 125 for that. So in other words, you would notice that it simply means that for the next question, okay, which is right here, our calculation is going to show us 125, because that is the number of successful trials for over 1,200 hours of lasting bulbs. They're divided by the total number of trials, which is 250. And when we perform that division, I am sure we all agree that the answer is going to give us 0.5. So this is definitely equal to 0.5. 0.5. Okay, so I think we're done with that. That was not too bad. Okay, that was not too bad. All right, so we are done with that. Finally, we have another question over here. And the question that we have here is talking about a shop buys 2,250 of these light bulbs. Estimate how many will last longer than 1,200 hours. We all remember that to do this, they are not asking us for the probability anymore. Okay? Because previously, from question B above, which is this one here, we already know the probability of bulb lasting more than or longer than 1,200 hours. So what they want us to estimate is that total number of successes, like how many bulbs will last longer. That's what they're asking now. So if you already have the formula that relative frequency, let me shorten it, relative frequency is supposed to be equal to number of, so let me put it that way, number of successful, based on this example now, I'm going to call it number of successful bulbs, just to flow with what the question is talking about. Okay, we're going to expect that to be divided by, based on the formula of relative frequency, divided by the total number of bulbs. Okay, divided by the total number of bulbs. Let me shorten the number here of bulbs. Okay, so in this case, what do you see, guys? I can see that from what is going on here, the relative frequency, basically, okay, the relative frequency basically over here all right, has been given. So I can work with this by saying that the next thing here is now that 0.5, which is the relative frequency we calculated. It's a continuation, guys. Don't forget, I'm just trying to, okay, so let me put a comma here so that I know that it continues from here. 0.5 is actually the relative frequency for bulbs lasting longer than 1,200. So that is the relative frequency I need to use here. Anytime I mention relative frequency, understand that I'm also talking about probability, estimated probability. Okay, not the actual one, the estimated probability. So 0.5 is going to be equal to, based on the formula we've written down, what is the number of successful bulbs? That's what we are looking for. We need to know how many. So we don't know that. So if you use the variable x to represent that, 0.5 equals to x, and then divided by, okay, x divided by, what is our total number of bulbs? How many bulbs did the shop buy? So I have 2250 over there. So the total number of bulbs there is 2250, which shows that to calculate x, which is representing the number of successful bulbs, we're going to expect that, okay, let me put a comma here as well. We're going to expect that when I cross multiply, okay, when I cross multiply, I'm going to have the value of x to be eventually equal to the product of 0.5 and, so let me put a space and put times 0.5 times 2250, okay? So that can tell us that something is going on there. I might want to change just for proper, no mistake in the liberty. Let's change that to, let's use B as the total number of balls there. Let's use B. So I'm going to change this to B, so that we don't mix the multiplication sign I use here for the other one. So if you multiply that, obviously, you're going to land your final answer to be equal to 0.5 times 2250, just half of that. 0.5 times 2250, you are going to get 1125. So 1125 is the number of bulbs we're going to expect, okay, to be successful out of the 2,250 bulbs that we have here. Okay, putting that down very quickly inside the box, 1125, and then we mark it all correct. Well done, perfect score. Now, I want us to focus on what happened over here. Let me use, okay. Let's focus on what happened here. Do you realize that 0.5 is the relative frequency or estimated probability, and 2250 is the total number of bulbs, and B is the expected number of successful bulbs. So that means we can create a formula anytime they ask us for expected number, or we should estimate the number of, you know, successes in our experiment. So please take note of that, guys. I could write a formula, but then you can provide that from what we have there. We're going to see what's going to happen later. Here is a spinner. It spun 900 times, and the color it lands on is recorded. Okay, the table shows how the spinner landed. Work out the relative frequencies for each color. So it's going to be, like I told you, relative frequencies is also talking about probability, but the estimated one. So for red, the frequency is 108. Don't forget that we have the total number of times it was spun, which is the definitely the total number of trials. So the probability is going to be probability of the color red is going to be the number of times the red showed up, which is our success for red, divided by the total number of trials, which is our 900. So guys, work on the calculations. 108 divided by 900, what do you get? You should get 0.12. 0.12. Then you go for the next one, 306 for green. So that would be 306 divided by 900. Divided by 900, you should get 0.34. 0.34. The next one, for blue, you are going to be calculating 81 divided by 900, and that should give you 0.09. 0.09. And the next one is for pink. And for pink is 189 divided by 900. Okay. And that should give you 0.21. 0.21. And then the last one you have for yellow, 216. So you have 216 divided by 900. 216 divided by 900 should give you 0.24. So you have a 0.24 right there. Okay. So we all know how to calculate relative frequencies now, or simply call it estimated probabilities. And if we mark it, we have it all correct. Now, the question here is this. Is this a fair spinner, or do the results suggest that it is biased to land on some colors more than the others? Remember that for any event to be fair, you expect all the frequencies, the number of times, okay, to actually be close to each other. What I'm looking at, I can even see 306 in my frequencies here for green. I can see 216, 81 low for blue. So this is not fair. We have to consider how many spins we were done. After 900 spins, things should have evened out. Yeah, you know, even themselves out. Because the more the number of times you perform the experiment, the better the estimation of the probability. But what you're looking at here is, I'm sorry, even with 900 spins, we have values too far from each other. So definitely, if they have not, that means if the frequencies here didn't even out, it implies that the spinner might be biased. Now, let us take a closer look at the spinner. See the spinner now? He's actually biased. Some of the edges of this spinner are longer than others. It is much more difficult to make it land on blue or red. Those are the smallest triangles that are actually not as big as the others. So it might not land there. Okay. The spinner is biased towards, yes, is biased towards green, the bigger triangle, biased towards pink, bigger, biased towards yellow, okay, pink and yellow. So that is that about that. Here we have the spinner, which is a regular pentagon. Regular pentagon, that means all of them are actually of the same sizes. I have the numbers 1, 2, 3, 4, 5 on that spinner. It stands an equal chance of landing on any of numbers 1 to 5. 4 friends took turns in spinning and recording how many times they got a 5. And this is what they recorded. One of the friends recorded their result incorrectly. Who was it? Who was it? Who was it? Let's find out. Number of spins, 1,000. Okay, I want to believe that after 1,000 spins, with 215, the number of fives, they were recording the number of times they got a 5. Okay, let's find out. Let's do the calculation. With 215 and 1,000 total number of spins, yes, relative frequency is 0.215, that is correct. 90 over 300, 0.3, 17 over 100, 0.15, 3 over 10, 0.3. So let's find out what the problem is. The spinner is fair, so the probability of getting a 5 is 0.2. So this is normal calculated probability. There are 5 numbers on the spinner. To get a 5, that is just one number. So it has to be 1 over 5, and 1 over 5 in decimal as a probability is 0.2. So relative frequencies here should be close to this 0.2. Okay, should be close to this 0.2. But with what we are looking at, we can see that both Christie's and Mikey's probability are close to 0.2. So we can cross them off. We are okay with 0.17 and 0.215. The issue now is with 0.3, which is Joel and Lee. They, both Christy and Mikey, they have most likely recorded their scores correctly because the answers they got are close to 0.2, which is the probability that's been calculated. Now, looking at Joel and Lee, both of them have probability of 0.3. Yes, we can see that, yes. This is where we have to look at the number of spins. You will see that with Joel only spun 10 times. This isn't very many. And so it is more likely that the number of fives will be would vary quite a lot. So we can understand that 0.3 should actually be far from the actual probability because the number of spins is very low. But when Lee is now doing 300 spins, Lee's probability or relative frequency should actually be closer. So there's something wrong here in this calculation right here. And where the problem is from the number of fives that Lee recorded. Because for Lee to get 5 90 times, it's less likely to be good luck. It could have happened, although, but after 300 spins, we would expect the probability to be closer to what we expected, which is 0.2. So Lee is the most likely person to have recorded his results incorrectly. Moving on. We have to click the buttons to roll the dice. The results will be shown in the table. If you roll 10 times, that's what you have. 100 times, see your result for the frequencies for the dice. Roll 300 times, roll 500 times. Okay. Look at the frequencies and the probabilities of the scores. Is this a fair dice? Of course, with what I'm looking at here, this one is not fair. After 500, 45 is still not close to others. 53, 2 is too far. Okay, this is not a fair dice. Let's roll 300, the same thing here. Let's roll 100, the same thing here. In fact, with low number of turns, you can't even be able to estimate. But with the 500 times, we can see that it is not a fair dice. It is not a fair dice. So let us show relative frequencies, as you can see. After calculating all the relative frequencies, see what we have. But if we are to calculate the expected probability, I'm sure all of this will be far from it. Now, until you have done a large number of trials, it is hard to tell. The probabilities won't be at all accurate unless you have done at least 300 trials. What do you think? Relative frequency says that we only know what the true probabilities are after a large number of trials. Surely this is a chance. The dice is definitely not a fair dice. It has been weighted to land on 1 and 6, okay? Hardly at all. And then 2 and 5 more often than any of the other numbers. The probabilities of each number are given. Do the relative frequencies match the probabilities? Of course not. So it is a dice that is not fair, guys. Finally, let's check for this one. Let me just go for a row for 500 times. Wow, can we see this? 87, 74, 87, 75, 93, 84. All of them not too far from each other. Let's show their relative frequencies. Not also far from each other. I might want to say that this is a fair dice. This is a fair dice until we've done, we've actually clicked on 500 times. So we expect it to be very close. Okay, let's find out. Let's find out. Yes, this dice is fair because it has an equally likely chance of landing on each number. Okay, so after many trials, we see that the probabilities definitely should be reasonably close to each other. And that has happened here. Okay, so we are good to go. So do the relative frequencies match the probabilities? We can actually find out, okay? Because after 500 times, let me just show you what they are trying to say there. Let's calculate for 1. If we are calculating for 1 by normal estimated probability, expected probability rather, probability of 1 is supposed to be equal to how many times did 1 show up in our dice? Let's take a look at it. It showed up 87 times. Okay, so because of that, we are going to have 87 divided by the total number of times we did it, which is 500. So if we do that calculation, what does it give us? Let's see if it is actually, it matches the probabilities. It matches the relative frequencies rather. So 87 divided by 500. By the time you calculate that, you're going to have 0.174. So it matches 0.174. So I challenge you to do the rest and find out if they also match. I will expect that they will all match. Okay, so that is it, guys, for today. A very lovely lesson, very interesting, understanding relative frequency. This is very good. So pick your lessons and then please remember to do your assignments on myimath.com. I will tell you and inform you about the assignment on Edmodo, which is where we drop all our activities. So please remember to do your assignment and do it early enough. Thank you very much for being attentive in today's class. I'm going to see you guys in the next class where we shall treat the next aspect of probability. Today has been a wonderful time with you guys. You are doing very, very well. So till next class, this is bye-bye from Mr. Ayodeji Ogunyeye. Bye for now.